Axel Ljungström speaks again, this time about the Steenrod squares in HoTT Revisited.
Thank you. Okay, thank you. Nice to be here. Right, so this is a very different, well, it's not very different, it's about cohomology instead of homology, so that's quite different. This is Steenrod, he's in a square, that was a joke. I was really short on time. Okay, so now we're leaving the cellular world. Phew, finally. We're in the world of Steenrod squares now. So this talks about Steenrod squares, and it's a construction on the usual nice representable cohomology theory in HoTT. So these were originally investigated in HoTT by Guillaume Brunery, and the goal of this project is essentially to finish what he started. So this was a types talk or types abstract from 2017, I think, and nothing was done after that. So me and David thought that it was about time. So crash course on cohomology, non-cellular cohomology in HoTT. The nth cohomology group of a space X with coefficients in an abelian group G is the set of maps from X into KGN, where KGN denotes the Eilenberg-MacLane space, the nth Eilenberg-MacLane space over G, and it has a bunch of properties. They're nice. So it's n-1 connected. It comes equipped with an equivalence between itself and the loop space of the n+1th Eilenberg-MacLane space. It satisfies that the 0th one is your group G. And it comes equipped with an invertible and commutative H-space structure. So you have some notion of addition on your Eilenberg-MacLane spaces. And it also comes, so whenever your group G is some commutative ring R, it comes with a graded commutative multiplication. So going from KRN cross KRM into KRN plus M. And this is called the cup product. So this was mentioned in Ulrich's talk too. Right, these operations immediately turn the direct sum of all of your homology groups into a graded commutative ring, whose addition is given by plus on Eilenberg-MacLane spaces, and whose multiplication is given by the cup product. Okay, now you know everything you need to know about cohomology. Well, you don't know why it's useful, well, you probably do, but it's useful for distinguishing between spaces. But of course, we're very sad, but this happens often. We might have two spaces that we're interested in, which are not equivalent, but still share the same cohomology groups, even for any R. Very bad situation. But fortunately, there are further invariants that we can consider, and one of these is the Steenrod squares. So the Steenrod square is an invariant that you get by specifying that your ring should be Z mod 2. So these are a set of cohomology operations. So the nth square goes from the ith cohomology group into the ith plus nth cohomology group. So Brunery defined these in HoTT, but he didn't prove really any of the properties describing these operations. So in this talk, we're going to revisit his definition, and we're going to slightly reformulate it, but we're going to revisit his definition, and we're going to prove the key properties regarding these Steenrod squares. So some notation, Kn will denote the nth Eilenberg-MacLane space. Everything is in Z mod 2 here. Hn will always denote Z mod 2 cohomology. Okay. Now, I said that the Steenrod squares were usually defined on cohomology groups, but because it's in HoTT, we like to work directly with Eilenberg-MacLane spaces. So I'm going to describe what they are on the level of Eilenberg-MacLane spaces. And this is kind of the main result or the main theorem, which is partially proved. This is still work in progress, but most of it is proved. So the theorem is that there exists a family of pointed maps, SQN, going from Ki into Ki plus n. So I'm sometimes going to write out the subscript here to denote the dimension of the domain, such that the 0th square of x is x. The nth square in dimension n is just the cup product squared. SQN of x is 0 if n is too large, and SQN satisfies the Cartan formula, which essentially says that the squares are, in a natural way, a ring homomorphism. So the squares take x cup y to a sum of smaller cup products, roughly speaking. Yeah, you can read. Then there's more, of course. There's always more. We also require our squares to respect suspension. So we want, whenever we apply the square from ki to ki plus n, this should be the same thing as applying the loop space functor on our square from ki plus 1 into ki plus 1 plus n. So that's an annoying axiom that we have to check. But even more annoying is the Adem relations. So these are, I mean, you're not supposed to read them. You're just supposed to look at them and you move on. We have kind of proved this. We've proved this, basically, right? I'll tell you more about it soon. So Brunnery constructed these Steenrod squares using the unordered smash products, using something called unordered smash products. For technical reasons, we've chosen not to use smash products, but we've used unordered joins. Morally, the same construction, just slight difference in implementation. So I'm just recalling now a bunch of results on RP infinity. There's a note by Ulrich, and there's also a paper on RPN by real projective space in HoTT by Ulrich and Egbert Reike. You can look at for reference. So I'm going to denote by RP infinity the type of two-element types, so types that are merely equivalent to the Booleans. And I'm just going to write x in RP infinity to say that x is a two-element type. And I always take the second projection to be implicit. Also, fact, there's a pointed equivalence from RP infinity to the first Eilenberg-MacLean space. And a last fact, if you have a two-element type x and a natural number, a family of natural numbers indexed by x, you can take the sum of these natural numbers. The idea is now to, so these are kind of unordered operations, this sum, for example, and the idea now is to obtain the Steenrod squares as a special case of an unordered cup product. So I use the word unordered, so what I mean, given a two-element type x and a family over x, if you look at a pi type over this family, then we can think of this type as describing the unordered pairs of A relative x. So in the special case, when x is just the Booleans, this is just the type, the usual product of A0 with A1. So what we have from previous work is an ordered cup product, which takes 2 points in kn0 and kn1, and it returns something in kn0 plus n1. Right? That's the usual cup product, and we would like to generalize this for an arbitrary x, for an arbitrary two-element type x, and an arbitrary family n over x. So this is what we want. It looks easy, but actually it's a bit involved because this doesn't exist automatically by just staring. You can't just see what this should be by staring at this type. In order to actually define this, we're going to need to throw on some structure onto this type, and then we can use magic. So structure first, then magic. And to get some nice structure on this type, we're going to use these unordered joins. So what's an unordered join? Given a two-element type x and a family over x, the unordered join of your family relative to x is this push out. So you take unordered pairs of x across your base space, across your two-element type, and you push out by mapping into the total space of x and into the unordered pairs of A. And the implementation here doesn't really matter. The key thing is that if you specify that x is the Booleans, this is easy. You can easily prove that this is the usual construction of joins in homotopy type theory. Okay. So what's the, wow, this definition too, I forgot about that one. So given a two-element type and a family of pointed types over your two-element type and another pointed type B, We can define the type of bihoms. I might have called them something else in the abstract, but now I'm calling them bihoms, which I'm going to denote by pointed maps from A to B relative X. And this is going to be the type of maps taking unordered pairs of A into B with some extra structure. And this extra structure, well, is this complicated thing. The key thing is that it's defined using these unordered joins. It has a very compact definition using unordered joins. If you want to make sense of it, you can try, but well, it makes sense. Doesn't matter because here's a fact. If we specify X to be the Booleans in our previous definition, then actually you just get the type of A0 smash A into B. And that's a nice type usually, because if B is very truncated and A0 and A1 are very connected, then this is usually of very low H level. Right. Okay. Now, the type of bihoms over a family of Eilenberg-MacLane spaces will have some especially nice properties. So the first property is that if you look at the family of bihoms over Eilenberg-MacLane spaces, this is always just Z mod 2. And Z mod 2 is a nice type. It doesn't contain that many points. You can pick the non-trivial one, and let's just call it the unordered cup product. So under this equivalence, we just pick the non-trivial element, and we call it the unordered cup product. And we can quite easily show that when X is the Boolean, this is actually just your usual cup product. So that's nice. Now, notation, given an unordered pair of points in Eilenberg-MacLane spaces, I'm just going to write cup X in X of f of X to denote the application of this non-trivial element to your unordered pairs. Okay. So why is this interesting? Well, the idea is that we can obtain the Steenrod squares by taking some form of diagonal of this unordered cup product. So the idea is that if you fix a natural number m, and you fix a point in the mth Eilenberg-MacLane space, and you fix a two-element type, you can construct two functions. A function from the naturals, from the x to the naturals, just constant, and x maps to m, and then some unordered pairs over Kn by just saying that it's constant A. So I'm taking a very trivial n and a very trivial f here, but why not? I can form the unordered cup product over this trivial looking thing, and I'm going to land in K2m. So what have we actually done here? Well, we have constructed a map from Km into Rp infinity into K2m. So why is this interesting? This is not at all the type of the Steenrod squares. Well, if you look at the codomain of this guy, you can show in general that if you have a bunch of Eilenberg-MacLane spaces, K0 up to Km, there's a natural map going into the mapping space from Rp infinity to Km, defined essentially by mapping points here into some form of polynomials on the other side. So it's a very nice map. This is the key point. It turns out that this very nice map is an equivalence. So I mean, this is not at all due to us, but we have proved this in HoTT in a previous paper, in a recent paper with Anders, and it's been formalized and all that. So that's a nice result. Okay, so key point being the codomain over there is just a sequence of Eilenberg-MacLane spaces. So actually, well, we define the top map up there, but we can just compose with this equivalence, and we're going to get a map that I'm going to call SQ hat, going from Km into K0 up to K2m. Now we're approaching the right thing, because we can now define the Steenrod squares by just saying that SQn, a map from Km to Km plus n, will just be this map composed with the m plus nth projection. If this makes sense. If it doesn't make sense, we just say that it's 0. And that defines the Steenrod squares. So it's a very strangely roundabout definition, considering how easy other things are to define when it comes to cohomology in HoTT. But the Steenrod squares, they have a very roundabout construction. Right. But now what's nice is that we defined our Steenrod squares as a special case of this weird unordered cup product. And this means that statements about the Steenrod squares will be, we can translate them back into statements about this unordered cup product. So in particular, we can try to sort of reverse engineer and translate back the Cartan formula and the Adem relations onto the level of unordered cup products. And they both turn out to be special cases of the following sort of master theorem, which says that given two element types x and y, and a family indexed by these guys, a family of natural numbers indexed by these guys, if you have any unordered quadruple f, if you can cup over f in two ways. You can first cup over x and then cup over y, but you can also cup over y and then cup over x. We're saying that these two things are equal. Looks very trivial, right? You just need to commute something. Well, it turns out that since we defined our Steenrod squares in terms of this weird unordered join, it turns out that this, in turn, is just a special case of the following trivial-looking theorem. I shouldn't have called it a theorem if it was trivial, right? But for any x and y in RP infinity and any family of types living over living over x and y, there's a function, not even an equivalence, just a plain good old function going from the join over A to the join over A, where first you take the join over x and y, and then you take the join over y and x. So there's some sort of Fubini-like theorem, but we're just asking for the map. This turns out to be the key theorem that proves everything. Well, okay, but then of course when you reach this point and you look at it and it looks so incredibly trivial, this was the absolute main obstacle to formalizing our proofs. So if someone sees why this should hold, we think it's trivial, please send me an email or talk to me. So what I noticed when I tried to sit down and formalize this was, well, when you start trying to describe this map from left to right, you end up in a situation where you have to understand the pi type over unordered joins. Pi type over a co-limit, it's not an obvious thing. And then, well, David came up, you can just use this hit to approximate this type. Well, this hit, of course, has a billion constructors, and all of this turns out to be very, very long and horrible, and it's over 2,000 lines of code just to describe this function. Also, I even changed the model of RP infinity just to be able to describe this into something very ad hoc. So very, very horrible stuff, but it holds. It's been formalized. So this has been formalized. So I said that the Adem relations and the Cartan formula are both consequences of this. At least we know this classically. They're very algebraic arguments. So what about the remaining axioms, things like suspension and all of these things? Well, it turns out that either they're trivial by definition, or you can show that they follow from the following conjecture. So it's very silly to have this as a conjecture because it looks so trivial. Given a point x in K1, the zeroth square of x is x. This should be very easy to prove, of course. And we do have a proof sketch, but we have no formalization yet. And this is also funny because then actually you can view SQ0 here as living in H1 of K1, which is isomorphic to Z mod 2. So actually, if you want to prove that all you need to prove is that SQ0 is 1 under this equivalence. So actually, you have yourself a Brunner number. Again, and does it compute? No, of course not. This is the ghost of Brunner. So we also have a direct construction of the Steenrod squares. Do I have time? Barely. Let me do it anyways. So there's you can sort of the specification of the Steenrod squares given in our theorem sort of suggests an inductive definition of the Steenrod squares. So what you want is something of that type, from ki to ki plus n. And what you can do is you can start defining it by induction on I. So in the base case, it's trivial. You only have two choices. And in the case I greater than 0, you define it by case distinction on n and I. And you know exactly what to do in case when n is greater than I. You know exactly what to do when n is equal to I. And then you have a question mark when n is less than I. So what we need is a map from ki to ki plus n. It's going very fast, sorry about that. But what's known is that the map from ki, taking a pointed map from ki into ki plus n, if you apply the loop space, you apply the loop space functor, this is actually an equivalence when I is less than n minus 1. But we can do better. So David proved in a recent paper that actually, in the case when I is less than n, well, you don't quite get an equivalence, but you get that it at least has a left inverse. So what this tells us in our case is, because we want to map from ki to ki plus n, well, it's enough to construct a map from omega ki into omega ki plus n. And, well, you can define it using the induction hypothesis and these two equivalences. And we're done. So, I mean, I gave you a very long construction before, and I'm giving a very simple one. Why didn't I just start with a simple one? Well, it was very nice and cool and very hot. You know, it's just delooping function spaces and all that type of stuff. But there's just no way to prove these things. We don't know how to do it, so that's why. But I think it's worth mentioning because it's a very hot construction. I'm just mentioning it because I had time. Okay, so a future ongoing work, finished formalization of all the details here. We should develop the theory of Steenrod algebras in HoTT, and we should absolutely think about higher Steenrod powers. So we define the Steenrod squares, but there are also higher powers for other prime numbers. It's very unclear whether our techniques generalize. So on that positive note, I say thank you for listening again.
Okay, questions?
So you had this conjecture 1, and you said that these things follow from the conjecture, right? Did you formalize that they follow from the conjecture as well?
No. but that's a fairly...
Or is it immediate, basically?
I think it's a pretty direct argument, yeah.
Okay.
The paper argument looks nice.
Okay.
I'm not too worried about that one. I'm more worried about other things.
Thanks.
More questions? So one from
I
me. Oh, the internet.
Oh, shit. Right. Yeah.
Could I just make a comment while the slide is displayed? Classically, this property that squares 0x equals x is actually a very difficult thing to check in some situations. And there are some situations where it's false. There's a version of the Steenrod algebra that doesn't have that identity, and that's the thing that acts in certain situations. So it's actually not completely implausible that this could be false in general. I'm not sure, but it is actually one of the most tricky axioms classically.
No, right. Yeah, I agree with you. But it looks trivial, of course. But no, I agree. I mean, so what you need to show is, I mean, you can give a very explicit definition of the zeroth square. It's just the commutator map, essentially, or it's the proof, the witness of the fact that the coupler is commutative on the diagonal, right? So essentially what you need to do is you need to prove that a certain commutativity proof is homotopically non-trivial, which is, yeah, when you think about it that way, it's quite clear why that's hard in this case.
Maybe one very short question. Doesn't seem to be the case. So let's thank Axel again.
Thank you.